thank you everyone for attending. This is the second half of the sparse and graph workshop in Julia. Our first speaker, Huda Nassar, is a senior computer scientist at Relational AI working on graph algorithms. Huda earned her PhD from Purdue University.
Okay, let me try. Can everyone hear me? Okay, good. Hi, everyone. So good to see so many of you here. First, just a quick intro about me. My name is Huda Nassar. As Willow said, I work at Relational AI. What I do at Relational AI is build graph algorithms so that our customers who want to use our product, if they want to run graph algorithms on Snowflake, that's basically the graph algorithms that me and my team work on. But for today, I'm actually going to talk about something completely different, still graphs, but nothing related to Relational AI. I'm going to talk about the graph of Julia, and just a quick disclaimer in the beginning. When I first started preparing for this talk, I had in mind to talk about more in-depth graph algorithms, how they're easily implemented in Julia, how Julia is really well suited to implement graph algorithms. And to do that, I wanted to get a fun data set to work with. And that fun data set ended up being the package dependency graph for Julia. But then I realized that data is so valuable, it's really, really fun to explore this data. So I kind of shifted the talk a little bit, and I'm talking more about the data and less about the algorithmic aspects of it. But I'm sure in this mini symposium, there's a lot of talks about algorithms too. So you'll hopefully get a bit of everything. And this is work with my PhD advisor. I guess he's continues to be my PhD advisor, and someone else, Claude. I don't know what's the best way to attribute recognition to AI assistants these days, but Claude helped a lot with this presentation, and I'll call out where Claude helped. Okay, so there will be three main components for this. Actually, let me set a timer before I forget. Okay, there will be three main components for this talk. I'm going to cover just kind of the relationship between graphs and linear algebra a little bit. I know that we have a diverse audience. I know most of you do know the relationship, but I just want to make sure that whoever doesn't just kind of sees the connection early on. And then the bulk of this talk will be about the Julia package dependency graph. We'll just kind of experiment with a few graph algorithms on these graphs. I would love for this part to actually be more interactive. So if you're sitting and you're like, oh, can we try this thing? I have the code ready and we can run things. I'll run things towards the end of the talk anyway. So feel free to ask these types of questions. And then at the end, I'm just going to end with, well, the demo will be kind of also in the part of the Julia package dependency graph, and then I'll talk about some notes and next steps. All right, so graphs and linear algebra. Just take a few minutes to talk about this. This is actually a screenshot I took yesterday from a talk I gave at JuliaCon in 2016. And back then, I was talking about a new package that I was working on called Matrix Networks that is also a graph algorithms package. And what I was kind of trying to make the point there was many operations we want to perform on networks or graphs are, in fact, linear algebra. And you can see a bunch of network operations you might be interested in, and maybe the most familiar to people is ranking. Example, PageRank. PageRank is nothing but a linear algebra equation. And so because a lot of the problems from graph theory maps so nicely to linear algebra, we can actually use linear algebra to solve them. And the fun thing is that the one thing I would add to this title is that Julia is pretty good at linear algebra, and that's really what makes it so attractive to write graph algorithms with Julia. And just to make the point a little more clearer, I got this example from a link that I linked below. But basically, the idea is if you have these, you can think of matrix multiplication as traveling along paths and graphs. So if you have, this kind of bipartite graph between the green and the pink dots, and then another bipartite graph between the pink and the blue dots, if you want to compute this mn, and let's say I want to see the distance between the path between x1 and z1 here, basically this node here and this node here, that's the value over here, and that's the edge, the number that will be on this edge here. And that's really nothing but -1 times 5, that's -5, plus any other way I could reach z1, and that's the only other way is 2 times -7 in this case. So it's really 2 times -7, that's -14, plus -5, that's -19, and then that's how we end up with MN. So matrix multiplication, for instance, and graph traversal are very, very, very tightly connected. And there are so many problems like that. All right. And with that, I hope everyone is on the same page at this point. Graphs, matrices, similar. Julia is good to write graph algorithms because it's good to write linear algebra. So we're in that space right now. So let's talk a little bit about this Julia package dependency graph. I'll be switching back and forth between slides and demo here, so just bear with me with the screens. All right, so this is where all the code is, Julia package evolution. You'll see contributors here. This is one call out to Claude, because a lot of this started out as trying to vibe code. And this was a really cool project to actually do with Claude, because there's just like a lot of ways. It's interesting. Like there were a lot of ways where like things could have taken us much longer to actually get done, and Claude would do it just so quickly. But there were a lot of pitfalls, for instance, as well. So one pitfall was like this understanding between the general and metadata.jl and trying to explain to Claude what happened there. Like some packages are, you want to get them from the Julia registries, and then some want to get them from another place, and like the formatting is different as well. So just wanted to explain that to Claude, and that took a little bit of time of back and forth to get this right, but that it was right at the end. There's more than 12,000 packages, as some of you might know, in the ecosystem. So all of this data is represented in the data itself. You will see there's a monthly snapshot. So since 2012. There's literally a monthly snapshot up until May 2025, where you can say, okay, let me just grab the graph of dependencies. And they're all indexed the same way, so you don't need to do any mappings. And you can literally just compare a graph from 2012 or 2013 with a graph from 2025. I want to click on it just to make sure I haven't missed anything major. Yeah, so tracking the package dependency over time. Complete history. There's a transition. There's ways, instructions on how to regenerate the data as well. And this is kind of how it works. We first identify the relevant commits, both in registries in each time interval. And then, yeah, we basically create this consistent package index across both registries so that we have the same packages basically having the same labels, generated sparse adjacency matrices, i.e. graphs, for each time point using the consistent index. And yeah, basically, and then if you go to matrices fixed, you will see, oh, that data is actually not here, but I have it on my, I'll show it in a second. Okay, I think that was too big to put here. But anyway, there's instructions on how to generate it, just basically following steps 1 through 4. Okay, going back to the slides. I feel like I just lost my slides. Oh no, they're here. Okay. So this is just kind of a high-level overview of the data itself. And so with that in mind, we basically have, at this point, snapshot at every month. And you can think of all sorts of questions to ask about this data. The first one that I think many of us could think about is PageRank. PageRank is a very common graph algorithm that I'm sure hopefully most of you know about. And it's an interesting way to understand importance and influence in a network. And my favorite example to try and illustrate why PageRank is relevant is like, if I want to think about, let's say, a social network where 2 people are famous and they have so many connections, and there's one person in between them, let's say, that connects that this person knows both of them, it does sound like, oh, this person only knows 2 people, so maybe that person is not that influential. But hey, that person knows the 2 most influential people in this network, so that person actually is influential. So there's this relationship between your influence is kind of dependent on the influence of your neighbors, and the influence of your neighbors depend on their neighbors, and so on and so. So this idea of global understanding of the graph, PageRank really illustrates that type of centrality really well. And so here, you're going to see the top 10 packages from a long time ago, up until today, you might start to see some patterns. Some interesting patterns will start to show up more and more. For instance, Compat was pretty strong, had a pretty high PageRank for a very long time. And you'll see when, any guesses when that will drop? 2018. Why? Yes. Yeah, you'll see that happen in just a little bit. See, it's starting. The other two are starting to kind of creep up, and Compat will soon start to kind of fade away. And then statistics seems to be a top value, a top PageRank value for some time. And so yeah, it's quite interesting to kind of see how things come and go over time. You know, like Compat was there and was the highest PageRank value by a very clear differential, but then eventually, because things changed in the ecosystem, Compat started to have a lower and lower influence in the graph. The colors I just left, so I wanted to identify 3 things that like you could clearly track. And these 3, like everything is purple except the 3 that are highest PageRank value most recently. So like if you see here, the highest are, oh, well, I guess no, I didn't do that. I thought I wanted to do that. But anyway, basically it's 3 packages that I was interested in kind of showcasing so that you can easily track them. Yeah.
Is something to take away from the fact that dates has the highest PageRank now? Like what, you have some intuition, or maybe it's just a random artifact of the algorithm?
Yeah, I honestly don't necessarily have a strong sense of why dates is like that. I'll show Betweenness centrality in a bit, and that result is way more like evident, and it makes a lot of sense. But for dates, I couldn't, like, I don't know. If anyone has actually hypotheses, I would love to hear it. Like, I personally couldn't think of something why dates has such a high PageRank.
So I was going to suggest, I was going to suggest that it would be great to run this and remove the STD list from.
That's fair. Yes. Yeah.
Are test dependencies included? Did you mix them in, or are they excluded?
Test dependencies. I can't remember. There is a way to exclude them, but I think actually it has everything. This data has everything. Yeah. Does that relate to a hypothesis you were trying to?
If you just look at depths, it's not the test dependencies. So you would have to look at extras to actually include the test dependencies.
I see. Okay,
If
then
you don't
maybe
look at extras,
it's,
then it's not including.
yeah, then it's probably just depths. Yeah. Okay. Yes. Yeah. Yeah. Okay, I will move on to the next. This is just kind of to show you the most recent 2025, May 2025 results. Betweenness centrality, basically we're running the same exact experiment, except that now we're trying to get betweenness centrality on this graph over time. And the way I would like to usually describe betweenness centrality, well, actually it's pretty straightforward. I can just read this part. The higher the betweenness centrality value, the more the package is on shortest path connecting other packages. And the reason I just said you'll see how the result makes sense in a bit is because I think there's a group of packages where so many packages depend on them, and at the same time, this group of packages depend on so many other packages. So they are kind of like the in-between of paths between point A and point B. And in a bit, I don't want to, actually, any guesses what collection of packages we'll have? Well, it's already showing up. But the plotting packages actually have the highest betweenness centrality scores. Plots already showed up, GR is there, and then you'll see Maki kind of make an entrance here. And yeah, eventually you'll see that the 3 of them will have the highest betweenness centrality scores. Yeah, go ahead, Viral.
I'm assuming this is undirected.
This is directed, actually.
Oh,
Yeah.
and yet plots is on the shortest path.
Yeah.
It's depending on plotting packages, I guess, like meta plotting packages.
Yeah, there's actually many packages depending on plotting packages. It's kind of surprising. Yeah.
We don't have conditional dependencies don't exist yet. So if you want your package to make a plot, it has to depend on plots
Yeah.
until way late, right?
Yeah, thank God.
And also plots has a legacy, right? Like a lot of people started using plots early on and like it's in their, like if even they wanted to visualize just one tiny result, they needed plots in their package, and then that's depending on it, and then probably they didn't bother change it because it's maybe a simple thing they wanted to show. So, yeah. And then just also for reference, this is the most recent, well, the data is up until 2025, May 2025, so May 2025's result for Betweenness, centrality plots, GR, and Maki are the top 3. All right, triangles, cycles, this was just kind of, I wanted to circle back to this idea of matrices and graphs. What's an easy way to identify if a graph has cycles in it? This is a really easy way. So you have, in this case, you have a very simple graph. You have 3 nodes, 1, 2, and 3. And you can represent this matrix as an adjacency matrix, 3 by 3 adjacency matrix. Row 1 is node 1. It only points to node 2. Node 2 only points to node 3. And node 3 only points to node 1. So this is very 3 by 3 simple graph. What happens if I multiply m by m? When I multiply m by m, I'm basically asking the question how many, basically any ij index here will mean that I have a path of length 2 between I and j. So m times m in this case, this number is now 1, which is saying node number 1 is pointing to node number 3. And that's right, because I can go from node number 1 by 1 edge, a second edge, and I can reach 3. So by just 2 edges, I can reach 3. Now, by 3 edges, I can reach 1. And that's a very straightforward way to understand whether there's a cycle of length 3 in the graph or not. I just multiply the adjacency matrix 3 times. And then if I find any entry, oh, this is the wrong matrix, sorry. This should be all ones on the diagonal. Then if I find any entry, like fixing it should be easy, so I'm bothered by it.
And you want MM at the top.
Sorry?
You want M cubed.
That's right, thank you. Yeah, okay. Here we go. So m times m times m is going to be this diagonal matrix, which basically is saying, okay, well, I can reach 1, 2 to 3 by 3 steps, back to 1, that's 3 steps. So the good news is that there are no cycles, which I hope that is something we would expect. So yeah, no cycles in the package dependency graph. Okay.
If you would actually find someone, that would be funny.
Yeah.
I have a question about that.
Yeah.
So you're talking about this as though it's packages depending on each other, but that's not really what happens. It's versions of packages. Versions depend on packages, and then packages have versions. So have you thought about how to represent that as a matrix? Or
Yeah, that's a great question. It is very complicated. Yeah, we tried to have Claude actually help with that, and that did not go anywhere. Yeah, we tried, like, yeah, it's, I think this project kind of started as like, oh, let's just get the dependency graph, like, fun little thing. And then like one thing after another, it's just like we're finding out all these problematic, kind of more complicated corner cases. Yeah, I don't have a solution to it, but I think that's a really good path to grow this data. Okay, clustering coefficients. So just kind of a quick idea about what clustering coefficients are. Clustering coefficients kind of say, if I have a high clustering coefficient, that means that my neighbors around me have a high likelihood to cluster together. And what that means in the package world, it means that basically if I'm part of a like if I am a package, I end up depending on, like, I basically have another package in my project, and we kind of like, we end up forming a clique. We end up forming kind of a cluster together. And I'm imagining there are types, well, you'll see some of the data, some of the packages do, there's a lot of packages that kind of depend on each other a lot. But the good news is that there isn't a ton of them. So it's not like our package ecosystem is like, oh, there's a package group here, package group here, package group here. There's a bit more. If it was very heavily clustered, that's kind of like not like that. That is, I wouldn't say that's a great signal. And just to kind of clarify what this plot you're seeing on the screen here is, Basically, clustering coefficients in the directed case, you can think of triangles as two ways, well, multiple ways actually, but the two that I chose here is the in triangles and out triangles. So in this case, I'm trying to find the clustering coefficient of this node, and I'm saying, okay, there's two packages that are depending on me, and then one of them is depending on the other, whether in this direction or that direction. And most packages had a 0 clustering coefficient value. Even, like when I ran it on this data set that is the most recent May 2025 one, there was roughly 1,600 of them, or a little more. 1,600 out of 12,800, that's like not a crazy number. But it's also interesting to see how the non-zero values have grown over time. So most recently, there's only about 1,600 packages that have a clustering coefficient higher than 0. And even early on, there wasn't a lot of them. So that's one scenario. But you'll see, okay, and then this is just kind of some results, but I'll skip this part. You'll see the out triangles counterpart has a lot more of this pattern, where basically the clustering coefficient here is I am a package, I'm depending on two things, and then there's a link between them. In that case, there's much more, like 6,000, but still that's not a ridiculously crazy number as well, given that we have about more than 12,000 packages. But that's just a way to understand that, okay, well, there are some groups of packages in the ecosystem that does kind of end up clustering together, but there's not a crazy amount of them. And this is just the results. And then finally, I did want to talk a little bit about some dependency graph of a given package. So for instance, you can see here, this is, I think, the graphs one, but I can get the Maki one, and let's hope this works. It does. And this is actually pretty interesting. So this is Maki. And if you look at these packages over here, these are all the JLL packages. Well, JLL wrappers. You'll see they kind of cluster together here. And if I remove, yeah, it's kind of hard to. But basically, there's these two big clusters. I will try and show maybe something. Let me actually try this one.
So what do the clusters show? JLL packages like depend on each other?
Yeah, they're more tightly connected. Yeah. And these are, I think, the JLL, yeah. And then so this was graphs in 2020. That sounds. Oh, okay, sorry. Okay. This. Okay, so this is. The other thing that maybe like this type of visualization is helpful for is actually also understanding like over time, if you're starting, how far, for instance, this is graphs.jl, but like how many packages are starting to depend on, that's one number that you are, you can just go and see in your Git repo. But also you might be interested in like how long is your longest dependency, your recursive dependency, for instance. That is something you might want to be careful about if you end up finding one package that is, like you only need it for a tiny little thing, but it's bringing in all these other packages because of some reason. That's just some understanding that you can build about your own package, and in case like you want to go and implement that tiny little feature that you're using from a different package, you might just save time and every time you someone tries to install your package. So just some things that you can think about and kind of understand about your packages as you're building them. And then I have less than 5 minutes left, so I will wrap up. Go back to here. Just some notes and next steps. Snapshots will be, we are going to generate them for every commit. They can be generated daily or at whatever other timestamp people are interested in. a lot more questions to be answered. I really barely scratched the surface here. Full data is, it said now available, but it's not, I guess. I just showed that. But it should be available very soon. And there's also, you can reproduce the data. There's steps to reproduce it in the repo itself, so that should be straightforward. And then the other thing is, time goes on, and maybe this data will be obsolete soon. So the idea is to hopefully try and automate updating this data over time. So yeah, and with that, thank you everyone for your attention. Thank you, Willow, for the organizing the mini. Yeah.
Yeah, we have time for a question or two.
Yeah.
Yes, I was expecting to see references to the graphs or metagraphs packages. Did you use those? And if not, how does your software relate to those?
I used graphs in the building of the building. Like, for instance, Betweenness centrality, that's how I used the graphs package. I used the graphs package to actually do the plotting as well, because it integrates very nicely with GraphMaki. So yeah, a lot of the internals, once you see the code, a lot of these packages are part of the code. Yeah, sorry if I wasn't super clear about that.